All right, thanks, Juan. Let me begin by thanking the organizers for giving me the chance to speak. This talk will be mostly about my most recent work with Tom Hartman, Juan Maldacena, Edgar Shagulian, and Amir Tajdini. And it's about understanding or deriving this new rule, which we call the island rule or the island conjecture. R here should be thought of, this is a formula for computing the entropy of the Hawking radiation, which is denoted by R, or a region containing the Hawking radiation. And what the formula says, that to compute the entropy of the radiation, one needs to consider contributions coming from islands I. Let me make first a few comments about the origins of this formula. So this formula follows from, if you assume unitarity and you follow the arguments of work with, oh wow, I forgot to write them here. Maxfield, Engelhardt, and Wall, and Marolf. And also from the results of Jeff Pennington, if you assume unitarity again, it was further justified by work with Mahajan, Maldacena, and Zhao, where we do this holography within holography inception business. And what it says, again, is that to compute the entropy of the radiation, there are contributions coming from these islands behind the horizon that fix Hawking's original answer. And as we saw yesterday, this talk will be about justifying this formula from replica wormholes. It's going to be similar to what Douglas and Jeff talked about, but now it's going to be in a more realistic model. So there's something, let me make a comment about this formula, something that you should keep in the back of your mind in this talk, and hopefully it'll become clear later. There's something weird in this formula. The fact that there's a von Neumann entropy appearing on both sides, but these von Neumann entropies are actually computing density matrices in different states. This rho Ri should be thought of as a density matrix in the semi-classical approximation. While the rho R here, the thing that we're trying to compute the entropy of, is sort of the exact density matrix of the Hawking radiation. Okay, hopefully this will become clear as I go along. To begin, let's apply this formula to a situation and see how it resolves the information paradox, or a version of it. This is the information paradox that appears in a toy version of the eternal black hole, but it actually also appears just in regular asymptotically flat, maximally extended Schwarzschild in any dimension.
Sorry, Ahmed, before I continue, could you just define the rest of that equation? What is min Ix and Xi?
Okay. So the prescription, okay, first point is that you need to include contributions from islands. How do you pin down the location of the islands? You need to first extremize this functional. That gives you a set of islands, or extremal islands. And then you need to take the one with the minimal generalized entropy, or this functional evaluated with that island. So it's very much like the usual Ryu-Takanagi formula. You look for extremal surfaces, and then you take the one with minimal area or minimal generalized entropy.
You might just say is the Ryu-Takanagi.
But I mean, it's kind of modified, right? I mean, okay, yeah, in spirit, sure. Okay, was that clear enough? Okay. Sorry, I was assuming things. Okay. So let's consider a hybrid eternal black hole, which is an eternal ADS black hole that is in thermal equilibrium with two flat space regions. Here I'm imagining that along the ADS boundaries, I have transparent boundary conditions for the matter theory living in the space-time. So the matter theory living everywhere is some conformal field theory. In this region in the center here, I have JT gravity. So to begin, let's work in the semi-classical limit. where we have a CFT on a fixed gravitational background, the quantum state of the CFT can be thought of as being prepared by the path integral on a fixed geometry, that being the Euclidean ADS2 and Euclidean flat space. This prepares the semi-classical Hartle-Hawking state for the fields, and this state I will call O tilde. So tilde always, for me, is going to mean sort of in the semi-classical description or the semi-classical state. This state has the usual pattern of entanglement between the sort of Hawking radiation. So you have Hawking modes outside that are entangled across the horizon as such, and similarly for the left movers. And now to see a paradox, consider computing the entropy of a region R that is the union of two half spaces in the flat space region. So let's call this region R. And we want to study this entropy as a function of time. We have two endpoints, so there's more than one way that you can evolve in time. Let's consider the one where you break the boost symmetry. So you evolve both points forwards in time as such. Now there's a quick argument to see that you'll run into a paradox. Basically, as a function of time, this interval collects more and more exterior Hawking modes that are entangled with their partners behind the event horizon. This means that if you compute the entropy as a function of time, you will find that it just grows linearly in time. Well, what I just said so far is just that the entropy increases. Now, why does the entropy increase linearly in time? This black hole is static. The temperature is fixed for all time, and the rate at which these Hawking modes are produced is controlled by the temperature. Well, it's just equal to the temperature, and so you expect a linear growth as such. It's controlled by C, the central charge of the field theory, times the temperature times time. Now, this arbitrary growth of the entropy of R is inconsistent with the finiteness of the black hole or the wormhole Hilbert space at a given energy, where the maximum entropy it can have is given by the coarse-grained entropy, which is twice the Bekenstein-Hawking entropy at the given temperature T. The information paradox kicks in at a time of order beta, SPH over C. Okay? So past this time, the black hole becomes overfilled. Let me make a comment which should disturb many of you, especially Dawn. If you look at this space-time after the page time, you can run the amps argument in this case. So there's a firewall paradox in the eternal black hole. So after the page time, so maybe before I do that actually, if we have unitary evolution, what we expect is that we expect a page curve. The entropy curve should grow as fast as it can for early times up until this time, which is the page time. Then the entropy should saturate to the coarse-grained entropy of the black hole. This is what we expect from unitary evaporation. Now, let's assume unitarity and look at the black hole after the page time. This tells us that the next Hawking mode to escape should not increase the entropy of R. But the only way that that can be true is if this mode is not entangled with its interior partner. So if you break this entanglement, you generate a firewall at the horizon. But this is absurd, because this is the eternal black hole. There's a boost symmetry. If there's a firewall here, there's a firewall everywhere. To me, this was sort of the final blow, to me, sort of final blow for firewalls, because I love the eternal black hole too much to believe this. But the island formula saves the day. So what the island formula says is that at early times, so let's just apply it here and look for island contributions. You find that at early times, the minimal extremal island is the trivial one, basically meaning there's no island contribution. And actually, at early times, there is no other candidate island, so the trivial island is the minimal one by default. At later times, however, redraw the horizon. Let me see. So at later times, you do expect the emergence of an island, and which extends through the wormhole and ends outside of the horizon. There's an annoying issue here, which is that the island requires us to compute the entropy of, to compute the entropy of R union I. That's a 2-interval entropy calculation, which is not universal. However, you can argue that at late times, or late enough times, you expect that this endpoint of the island would tend towards this corner, and this endpoint would tend towards that corner. And then you can make an argument that you have some sort of OPE limit that you can take between these 2 points and these 2 points, such that the entropy, the von Neumann entropy, factorizes, becomes a sum of 2 pieces. In fact, you get, let me erase this. So for this contribution, for the island contribution, you get SR island. It'll have the area piece at some location A1. This is one of the endpoints of the island, plus the von Neumann entropy. B1, A1. I guess I should have labeled, I meant by A's and B's. So the endpoint of R here is V1. The endpoint of the island here is A1 and A2 and B2. And so the entropy of the island contribution will be a sum of 2 terms. The same thing, but with A2, B2, and A2. Because the entropy factorizes into 2 terms, this means that the extremization procedure in this situation becomes a separate extremization for the left and one for the right. This means, was there a question? No. This means, so that fact coupled with the fact that we have boost symmetry means that the island contribution must be a constant. I'm going to draw it in blue. It's going to look something like this. Okay. Another thing is that I said that the endpoints are in some sense near the horizon but outside. This tells you how you will get twice the Bekenstein-Hawking entropy. These dilaton terms, or the area terms effectively, gives you twice the Bekenstein-Hawking entropy, or twice the area of the black hole. So we see how the island formula gives us a new possible contribution to the entropy. And now applying the minimality constraint tells you that the entropy as a function of time hops from this increasing answer to this constant answer after the page time. Okay, any questions about that? All right. Yeah?
Why was it factorizing?
Oh, so the first part of that argument is to say that we expect the island points to move towards this corner. Now you have an OPE limit between these 2 points when you compute the entropy. So this means that the entropy factorizes into the sum. So we were computing first the entropy of the union of this guy, and this guy. But because we have a global state here, a global pure state, that entropy is the same as the entropy of this region plus the entropy of this region. Yeah, so sorry.
Those two factorized.
Exactly. Those two factorize because of the OPE argument. And this means that the extremization procedure factorizes as well. OK. Ted?
Can I just make a question/comment? So the left-hand side of this new rule, if I were to look at it as field theory on a background, the answer would be infinity.
No. Why is there infinity?
Well, because there's a sharp edge at the end of R.
Oh, you mean the UV divergence here? Or do you mean this thing?
Yeah, just the exterior, like if you took R to run to any point, including at the horizon, there's just an infinite entanglement entropy in that region. And if I look at semi-classical Hawking radiation calculation with one end of R at infinity and one end on the horizon, it is constant because Hawking radiation is just peeling apart of pairs that are already there. So that infinity just stays constant in time. So it seems like what's going on, I mean, it must be that the left-hand side is the regulated version of that statement, but then that should be constant in time. So I'm kind of confused how to read the equation, the left-hand side of the equation.
For now, to make this argument, it is sufficient to subtract off the vacuum contribution. That's going to remove this UV divergence that you're worried about.
You can say it's on both sides, right? Because it's also in this SVN.
Exactly. Exactly.
So you can cancel it. And R does not go to the horizon. Yeah, R. It's more like an asymptotic.
Yeah. Correct.
But it still does have a shape.
Okay. All right. So we applied the rule to one situation, and we saw how it fixed things. Now let's talk about deriving the island formula. Okay, so to do so, we need to consider the full path integral of this theory, where so that's what I'm drawing here. This is in Euclidean space. In this path integral, we are integrating over all CFT and JT gravity configurations. The semi-classical Hartle-Hawking state that we discussed over there is a saddle point of this path integral, but we want to consider the full path integral. We want to use the Euclidean path integral to compute the entropy of various flat space regions using the replica trick. So this is the replica trick. You compute trace rho to the n, and then you take its derivative. And trace rho to the n should be thought of as the path integral on this replicated manifold, which I will talk about now. So let's consider several cases. Let's first talk about computing the entropy of a single interval. This is an interval which starts at some point B in the flat space region and ends on the boundary of the ADS space or the JT region. To compute trace rho to the n, we have to consider n copies of the system identified cyclically across the cut. And at this stage, we did not fill in what the geometry is in this region. Prior to doing that, it is convenient to work in the covering space where you do a coordinate transformation that unwinds the cut. And now we can sort of fill in the space-time. And here we have just the usual problem in JT gravity, but now with a boundary whose renormalized length has been elongated to n times beta. Now it's clear that the leading saddle here will simply be, the leading saddle of the gravitational action will just be filling in the spacetime with the hyperbolic disk. Now if you go back to these original coordinates, what you'll find is that the branch cut gets extended into the bulk in this fashion. So now you have a new branch point in the bulk at some location A, and this A will ultimately be fixed by the equations of motion. Okay. We can also fill in this space here, so we extend this to there. Okay. So the idea is that so you've modified the boundary conditions by putting this cut here, and you get a new gravitational solution in response to that. I will always call this replicated manifold Mn tilde, and the manifold here on the branched cover, or what I will call sometimes the theory on the single sheet, as Mn, where it's Mn tilde mod Zn. I am assuming replica symmetry throughout. Now this was a warm-up. The more interesting case to consider, which is relevant to the story that we were talking about there, is the case where we're computing the entropy of two intervals. Okay, so now I'm going to erase this. Okay, so we want to compute the entropy of two intervals in the flat space region. And these are two intervals that start at some point b and minus b and extend all the way to infinity. Over there, I had them at b1 and b2, but we can work symmetrically. Yeah. In this case, there are two simple replica symmetric saddles to consider. The first is where each JT region is separately filled in with hyperbolic space. Okay, so something like that. This I will call the semi-classical saddle. The other configuration looks something like this. Let me first consider the case for n equals 3. So computing the third Renyi, I have a geometry that looks something like this. Okay, so wormhole connecting the three JT regions, and the cut is something like this. Working on the single sheet again, the wormhole can be represented by a cut in the gravity region and two new branch points. This A1 and A2 in this spacetime, or in this covered geometry, is somewhere here. A1, the cut is the line that I'm drawing. In the back here, there's A2. Okay. Going along a trajectory like that takes you from one sheet to the next. That's a trajectory that goes like that. These points, A1 and A2, are the fixed points of the Zn symmetry. The interesting thing here is that these new branch points and branch cut has been dynamically generated by gravity. Okay. Any questions about that? Next is how to compute the entropy from the action. Okay, this is going to be basically a summary or review of just a standard story as told by Lukowitz, Maldacena, and also by Lukowitz and Dong, and also other papers. Yes.
You also have another pair of branch points outside.
Yeah, have branch points outside. That's the region that's the region R, whose entropy we were computing, and now we have new branch points inside.
So the outside one is also connected with the replica.
Yeah. Good. Yes, they're also connected. Yes. Okay, so to compute the entropy from the action, we just do the usual thing. So the entropy is just the derivative of the off-shell action, where you take and you take n goes to 1. The action, though we're considering the total action, it has a JT part evaluated on the replicated manifold Mn tilde, and also the CFT partition function also on the manifold, on the replicated manifold. Now the first step is to cast everything in terms of the theory on the single sheet, and also assuming replica symmetry. You can write the gravitational part as something like this. It's just a JT action on the single sheet, but because now we have these branch points, the metric is singular at these points, and therefore we add these cosmic brane terms. These are the things responsible for creating a conical singularity at these points. The matter action on the replicated manifold can be written as a correlation function of twist fields, or rather the matter partition function can be written as this correlation function. And one comment here is that these points A1 and A2 and so on, these are parameters in the gravitational configuration, as in they are ultimately determined by the equations of motion. These are not just put in by hand. Now, solving the equations of motion for this action for general n is pretty difficult in this model. The main complication comes from the fact that here we need to glue two CFTs, one inside the disk and one outside the disk. The procedure of doing this requires solving what is called the conformal welding problem, which I don't have time to discuss. And therefore, we can only solve this model perturbatively, either in n-1, working near n equals 1, or perturbatively in the gravitational coupling, where we can actually find the solutions for the Renyi entropies, so the gravitational coupling is small at high temperature. I will discuss just what happens near n equals 1. So near n equals 1, you have the following. This log is the n over n. So you imagine that you start with a solution at n equals 1. That's this part of the action. And then you deform slightly away by inserting this pair of branch points. So these twist fields and these cosmic brane terms. And three things happen. First is you get a deformation of the geometry. This term gets canceled because when you apply the equations of motion. And then you get, from the cosmic brane terms, you get the area piece, while from the matter action, you get the matter entropy. Now it's clear how taking the derivative of this gives you the entropy. And finally, we can also get the extremization condition by varying with respect to these parameters A1 and A2. That gives you the extremization condition. Okay. No, I mean, this is an equation of motion, right? So, yeah. So, I mean, these AIs, they're varying with respect to the A's is like varying with respect to the metric. Yeah. So it's clear how. now I'm going to go back to this point where we're using rho tilde. It's clear here that because we're working near n equals 1, that the entropy in this formula is to be thought of as being evaluated in the semi-classical state, right? The n equals 1 solution, the M1, is literally just the, here we have, again, flat space, but here we just have the Euclidean black hole. So we're really just doing the path integral now on the fixed background, but now in the presence of these cuts. And so we see how the prescription, it really gives you the fact that on the right-hand side of the equation, you have to use the semi-classical state, but now in the presence of these cuts. And I'm almost done. So what we have seen so far is that in the computation of trace rho r to the n, we get, okay, good. We get two contributions, where here we're imagining that we're summing over saddles, plus dot, 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 which we can't compute in this model, at least not yet. We have a contribution coming from this saddle, the semi-classical saddle, which gives us a contribution that decreases with time because the entropy of R increases linearly as we discussed before. The island contribution, if you recall, actually I forgot to mention it, or maybe I mentioned it, I forget, that at t equals 0 there is no island contribution. This calculation that we're doing is a t equals 0 calculation, right? So over here, and these equations, the solution of the extremization equations at t equals 0 don't give you a real solution. But so therefore, the saddle starts off complex, but as a function of time, as you evolve both of these endpoints to the future, this saddle becomes real at some point, and then is a constant. And therefore, we have a exponentially decreasing piece and a piece which is constant. And at some point, this term is going to dominate over that. And that is what gives us the minimality condition in the island formula up there. So it's this first order phase transition between these saddles. Okay. Let me make some comments. Are there any questions? Yes, Ning. Four black holes?
Four black holes such that they're entangled in some four-party GHD configuration.
Uh-huh.
And I'm a little confused as to the form of the entropy that you've written, because the area piece will, the area piece by itself will obey the holographic type inequalities. And if I'm understanding the situation being on random entropy for the semi-classical piece, it's based on cuts of this replica wormhole geometry, which also obey the holographic entropy inequalities. So the sum will also obey it for the obvious reason. But if I have four black holes that are entangled in a four-party GHD state, then manifestly that won't obey those inequalities. So I guess my question is, if I'm supposed to think about this as something that's true for quantum gravity states, either what makes the situation that I described not a valid quantum gravity state, or why should I think about this formula as only one restricted set of states?
Quick answer is I don't know. Second point is that feels like a question-answer period question. So let's, maybe I can make some more comments later. Yeah, because I want to make some comments before the end of the talk. Let me see. So there's an interesting situation. Oops. Okay. Where suppose you try to compute the entropy of the entire bath, including the boundaries. So now I'm considering something like this. Okay, so and so on and so forth. Using these arguments, it's not hard to see that the gravitational configuration, the leading saddle that respects these boundary conditions, is one where the cut is extended through the entire gravitational region. Okay. This means that this thing is equal to simply the Hartle-Hawking, semi-classical Hartle-Hawking state to the power of n, implying that trace rho to the n is equal to trace rho to the n is equal to 1, and therefore the entropy is equal to 0. I just thought this was a cute observation that I should mention, that Replica Wormholes tells you that the entropy of the entire Bath region with the endpoints is equal to 0. Somehow it sort of knows that everything in the bulk is dual to the flat space, the entire flat space region with the endpoints. Another comment I want to make is that for this discussion, even though for our calculations we chose to work with JT gravity, but that's just because it was simple. But we expect really that this should work for any gravitational theory in the bulk coupled to a flat space region outside. In fact, we had a paper out with George and Raghu Mahajan where we show, we find an example of this holography within holography business, but with 5 bulk dimensions and 4 boundary dimensions. So we have a black hole in 4 dimensions on a Planck brane coupled to a 4-dimensional flat space, and all of that is dual to 5 dimensions. And we also find islands, and the same story applies. The island resolves things in that case. But for this case at hand, really any theory that looks like JT in the IR will have these same solutions, and the same set of words would go through. You can take your favorite theory, maybe, I don't know, in 5 dimensions or 4 dimensions, that actually has a known single boundary dual, not a disorder average. And there are examples where, in that situation, where you have states, for example, these near extremal black holes that deep in the IR look very close to JT gravity. And finally, it would be interesting to run the PETS map discussion in this situation to show that the interior is part of the outside. I mean, you can say the same words that have been said for entanglement wedge reconstruction using JLMS and so on and so forth to say that the interior is dual to the exterior. The reason why the PETS map business would be interesting here is the fact that this island exists or becomes dominant after you evolve in Lorentzian time. So so it kicks in after some Lorentzian evolution. So it'll be interesting to see how the operator acting outside reaches the interior, but reaches the interior in Lorentzian space. And one final comment is that we've been working with large C just because we want to. We have these. We are sourcing the gravitational equations of motion with the matter expectation value of the stress tensor. So we work at large C because we want to suppress the matter loops. Basically, we want the location, the endpoint of these islands. Well, you might want to work at large C in order to say that the fuzziness about where the location of this island is small. But even for small c, this fuzziness is not actually a problem in situations like this, where at late times the island is large, and you expect it to be much larger than the potential fuzziness of the endpoints due to working with small c. And so we expect the same effect will, these islands and so on will play the same role, even in that case. And that's all I have. Thank you.